All right, so the last bit that we're going to talk about for angular momentum today is expanding on this idea that because Lx and Ly don't commute, once we have decided to know Lz, okay, then by definition we cannot know Lx and Ly. Okay, so like I said before, we focus on knowing our total angular momentum squared and the z component of our angular momentum. Okay, we tend to know those precisely, and then that means that we know nothing about Lx or Ly. Turns out that it's kind of nice to draw a picture of this. It's a little hard to kind of think about what that means abstractly, but we do have a pictorial method for depicting these different relationships between the various components of our angular momentum. Okay, and that's called a vector model of angular momentum. Okay, so let's do an example with L equals 1. Okay, so remember L is our angular momentum quantum number that we've seen before. Okay, so we know a few things about our system when we know that we have L equals 1 as our starting point. Okay, so we know that M sub L, or M, depends on L. Okay, so that's why it's called M sub L sometimes. So M, again, we'll often slip into calling it M sub L, right, can take on values of 0, plus or minus 1, plus or minus 2, and 2 plus or minus L. Okay? All right, so if we say that L equals 1 here, we know that for this case, our possible values of M are going to range from -1, 0, and +1. Okay, this is a good time to remind ourselves of the fact that each of our energy levels for a rigid rotor are 2J plus 1 or 2L plus 1 degenerate. So remember this from our spectroscopy lab. Okay, so again, analogous would be 2L plus 1 degenerate energy levels for our angular momentum. Okay, so if L equals 1, 2L plus 1 gives us 3. And how many values of M sub L do we have? We get 3 values of M sub L. Okay, so these shouldn't always match up with your degeneracy that you calculate from 2L plus 1. Okay, so we know some things about our angular momentum eigenvalues. Okay, so we know our z component. So if we look back to the result of this, we know that our eigenvalue for Lz acting on our spherical harmonics, we said, was mh bar. Okay, and then same for L squared. Right, we know that those values, eigenvalues, are L times L plus 1 times h bar squared. Okay, so if we plug in for our L equals 1 situation, okay, so plug in L equals 1, we know that our L squared eigenvalue is going to be 2h bar squared. Okay, and then we have our Lz eigenvalue of essentially minus h bar, 0, and plus h bar. We get 3 of them. Okay, so now we have all of the eigenvalues that we're interested in for total angular momentum squared, and LZ. And in fact, it's really the total angular momentum that we're interested in when all is said and done. So I'm just going to take the square root of this value. And again, we'll just take the positive root to have a meaningful result. Okay, so we have all of our eigenvalues. Okay, so we'll circle those. So we have L and we have LZ. Okay, so those are the two parts of our angular momentum that we can know exactly. Okay, so again, by specifying LZ, we now can know nothing about Lx and Ly. All right, so how do we put this together in a picture? Well, we're going to start with, change my color, we're going to draw a coordinate system. Okay, so we'll say that that's our z-axis, call that our y-axis, and we'll get an x-axis going through there. Okay, so here's our coordinate system, and we're just going to draw a vector diagram that describes everything that we have developed so far. Okay, so one thing to remember is, remember we have information about the z component of our angular momentum. Okay, so this tells us essentially information about how far up the magnitude of our z vector, part of our vector. Okay, so I'm going to make some little marks on there. So we'll say we get three options, basically 0, plus h bar, and minus h bar. Okay, so those are our z components. All right, and then we also know something about our total angular momentum vector. So that's essentially like the arm of the vector that's going to come out. Okay, so we know the length of that vector is square root of 2h bar. So we can just draw that vector. Okay, so let's say the length of that vector is square root of 2h bar. So that's our L. Okay. All right, so we know, it didn't quite go high enough. Okay, so vector goes as long as L, square root of 2h bar, and as high as our LZ. So as high as plus h bar, or we can do the same thing in the other direction, okay, for minus h bar. Okay, so now how do we account for the x and y components? Well, those are the ones we don't know. So to account for all possible values of x and y, what happens is we just essentially map out a cone around our z-axis. So we're going to basically account for all of the possible options for x and y. All right, so if you do your Pythagorean theorem, you will see that you essentially map out a circle of radius h bar that is centered at the origin. Okay, so we basically get something that comes out to be the shape of a cone. Okay, so we're getting that cone shape because essentially we are just mapping out, again, all of the possible values of the x and y components that we can't know precisely. All right, so if we could know x, y, and z components explicitly together, then we could just write one vector and be like, oh, I'm right here, right? But all we can know is one of those three along with our total angular momentum. Okay, so we've chosen to know the z component, so we know how high this vector is going to be coming up, okay, but then we don't know anything about where we're located in this xy plane. Okay, so that's where the cone comes from. Alright, so you should be able to draw one of these vector diagrams for angular momentum for any value of L equals anything, okay? So obviously L equals 0 is not going to be super interesting, but try your hand at L equals 2, and it will challenge your artistic abilities a little bit, but give it a try, and we can play around with that more later. But for now, hopefully this has been a good introduction to the different quantum mechanical considerations for angular momentum, and getting you accustomed to interpreting these vector model diagrams. Okay, so we're going to encounter angular momentum as we move forward into our hydrogen atom, so it's not going to go away. Okay, so we're just going to keep adding to it. All right, I hope that was helpful. Keep practicing those eigenvalue equations, and those vector models, and I'll talk to you later.